It's a very good afternoon to all of you. Am I audible and visible over there? Yes, good morning, good afternoon. Harsha, I have just entered now. Good afternoon. And how are you people doing there? I hope it is going great. Yes, a very good morning and good afternoon as well, right? It's all good. And how's the preparation? Is it going good? Are we revising the things on time and properly with the same enthusiasm which is required actually? Yes, I'm absolutely fine with them. Absolutely fine. Okay, now before, kind of rather than dwelling into something else, I hope everything is fine there at your end. No problem with the audio as well as the video, right? All of you are able to listen to me properly, see to me properly. Now, tell me what was the thing which we have done in the last class. I think we have learnt about predicting period, group, block number. That's what we have done. Now, Kavita is like chilling with studies, right? We have done that. Okay. So I think probably in the last class, I would have given you the atomic number. You have to predict. Okay. Now today, I'm just going to give you few electronic configurations and you try to predict from there. Okay. Is that okay? I'm going to write down the questions there. Make sure that you are also writing. And I may give you a little bit of time, maybe 5 to 7 minutes of time. And once you are done, we are going to discuss it. Okay. So let us go for the question here. Predict period, block and group number for the following. So I'm writing here neon 3s2 3p2, argon 3d5 4s2, helium 2s2, xenon 6s2, then xenon 6s2 4f14, radon 7s2 5f14 6d2, one more I am giving you here, radon 7s2 5f14 61. Please give it a try at your end. Need not write down the question here on this particular box, but you try to do it and then I'll discuss and you compare whether you have done it correctly or not. Is that okay? And my suggestion to you is whenever there are electrons in D and F, always count the total number of electrons. It is going to help you out. Why? Because the thing is, directly when you count the total number of electrons, you may come across that it may fall in the range of that 58 to 71, which straight away gives you idea that 6th period F block group number 3, or else 90 to 103, which gives you idea that again it is 7th period F block and group number 3. That's just my suggestion. Please go ahead and try to do it. And once you are done, let me know. Only one person has written completed. Here, I think Harsha, how many done? Harsha and Sujata, 2 persons are doing. Rest, I don't know, they're chilling. Sohan, 5th one. Tanishka completed. Okay. Sohan, 2 more left there, beta. 5th one you are doing. Harsha, Ishwar and Sujata. Geeta also completed. Shravanti also done. Okay, many students are saying done. So let us go ahead here. Now for the first one, you are able to see that here period number will be what? Period number will be 3rd. Okay. Highest principal quantum number, which is the subshell which is receiving the last electron. It is P. So the block is P over here. And in case of group number, I told you that for P, it has to be 12 plus number of NP electrons, which is 2 here. So group number has become 14 over here. Getting it? Now, for the next one, what is the highest n value? Highest n value is 4. So definitely your period number is 4. There is no doubt about it. But I know many people might have messed up in case of block. You tell me what you have written. Did you write down S or did you write down D? For the second one, did you write down S or D? Kindly respond, people who are in this app here. D. If you have written D, it is good. You must understand one thing, that the block here will be still D only. Reason being, examiner has tried to confuse you by writing the configuration shell wise. They may write down, they may club it together, but you should, that means they can arrange it shell wise. That means all the first shell together, then comes the second shell, then all the configuration of 3S, 3P, 3D they can write down together, and then 4S. But you should be aware that 3D will be filled up after the 4S is getting filled up. So actually what you should write down, you should be aware that it is actually argon, and then you know that argon marks the ending of 3rd period. You are entering into 4th period. So for the 4th period, you know that SDP is applicable. So you are going to write down 4S2 3D5. Are you able to understand? The examiner may give you, beautifully writing the entire thing. 1S2, 2S2, 2P6, 3S2, 3P6, 4S2, 3D5. Now they can also arrange it like this: 1S2, 2S2, 2p6, 3s2, 3p6, 3d5, so that students think that the last electron is entering into S. Are we able to understand that? Right? So you be careful, and in this particular juncture, that is just a way of representing, just writing all the configuration according to the shell wise, right? But you should be exactly knowing which one is the subshell which is receiving electron first and which one is receiving afterwards. So accordingly, group number here will be given as N is 4 here. So how many electrons in NS? 2 here. So 2 plus 5, I'll be writing this as 7. I hope everyone got this very clearly. Now next one I have written here, helium 2s2. So in this case, what I'm going to write down, period will be second, block will be S, and group number will be simply what? How many electrons in NS2? So group number should be 2. Good. Now for the fourth one also, the examiner has given you shell wise, that, right? So what you are supposed to do, xenon, you know that it is sixth, it is marking the ending of fifth period, so you are entering into sixth period. So you should be aware 6s2, 4f14, 5d10, and in fact you must count once the electrons also, just to be very safe there, that when you are in sixth period, is it corresponding to that range of 58 to 71 kya? You see here, this is 54, 56. 56 plus 14 is 70. 70 plus 10 is basically you are having 80. So that range is crossed here. 58 to 71 is only F block, right? So as such, now you can easily see that period will be 6. Just so that you do not make any mistake, okay? Then which block it will be? Block will be D block. And what about group number? Group number will be number of NS electron, number of N minus 1D. 2 plus 10, you are going to write down this as group number 12. Similarly, you count here. And here in this case, you will be having 82, right? And again, definitely you can see here 6s, 4f, 5d, 6p. So period number is 6, right? What about block here? Last subshell receiving is P block. Group number is going to be, for P block, 12 plus 2 here, you are having 14. 6p electrons, NP electrons. Clear about it? Now, with the 6th and 7th, for the 6th one, what you have done? 86 here, 86 plus 14, 100, and total you are having here 104. This is the element which I have given you. And you know that 104 is Rutherfordium, right? So you know that basically what period is 7th here. And what is the group number here? Last 2 digit you can write down, which is 4 here. And then block will be D block. Able to get it? This is always going to avoid any kind of confusion. Okay. Now, why I am always counting and writing for that F, especially for the last period, because it can create confusions here. I am writing here 86. If at all you do not count, you may end up writing this as D block element, thinking that the last electron is entering into D subshell. Okay. So now in this case, basically it is 86 plus 14, 100, and you are having total as 103. And you know that 103 is falling in the range of 90 to 103. And 90 to 103 is belonging to 7th period, F block, group number 3, right? So here this one is, period is 7th, block is F, and group number is 3. So be careful with F and D. Able to understand, everyone? Sashi, last one, what was your answer? What is the answer you have written? Sashi, Sohan here Harsha, and I think Ishwar. Those who are, Srivalli is also there. Shall we proceed further? Understood, everyone? So my suggestion to you will be, wherever you are having FND there, just make sure that you kind of just add the number 1 so that you can identify whether it is belonging to that F block series or not. Otherwise, you can just rely on what is the configuration given, and accordingly you can predict the answer. Okay? I know, that's the reason I have given it. I hope you understood now, Sohan. See, people who have made mistake, not to worry about. Unless and until you make mistake, you never learn, right? So it's absolutely fine. Only thing is you should be ready to learn. Okay. Now let us go ahead here. And I'm writing now IUPAC naming of elements having atomic number greater than 100. This is also there in your test syllabus. That's the reason I'm saying here. Now, as such, it is given on in your NCERT on page number 80, right? So the thing is simply before, kind of before the official names for different elements could be given, could be allotted to different elements, there was, there was the need for naming the elements, right? Like 101, 102. Now you know that it is Mendelevium, Nobelium, Lawrencium, Rutherfordium, like that. But earlier there has to be, how people will address which element they have discovered. So there were certain guidelines or, kind of certain rules which was given by IUPAC, which you have to follow, which I'm going to write here. So I'm writing here digit, name, and here it is abbreviation. So digit 0, 1, 2, 3, 4, 5, 6. This is very simple. That's why I'm little bit writing fast here. 7, 8 and 9. For 0 it is nil. For 1 it is un. For 2 it is bi. For 3 it is tri. For 4 it is quad. For 5 it is pent. For 6 it is hex. For 7 it is sept. For 8 it is oct. For 9 it is n. Do remember, normally people commit mistake at 7. For 7 you may write down hept, which is case of organic chemistry. Be aware that we are in inorganic chemistry, so we are naming it as sept, not hept. Okay. Now, whatever is the first letter, that is the abbreviation here. First letter is the abbreviation, right? So I'm writing here N, U, all simple one, all the smaller one you can write down. This is hex here. So you'll be having here B, then T here, then Q. You can have here P, you can have here H, you can have here S, you can have O, and you can have here E. Able to get it? Now, when it comes to name, let me go to the another one. So if you wish, you can note it down. Otherwise, you can simply tick mark in your NCERT, that particular table which is there, right? So now I'm simply writing the elements. Okay? And then you are having here name according to IUPAC nomenclature. Nomenclature means the temporary names which were given and official name. Okay. So I'm writing from 101, 102. Few of them I'll write down. Okay. As such, I've given you mnemonic for all of them. So I'm just writing for few of them. It is valid for rest of them. So the thing is, name should end with em, right? For 1 it is un. For 0 it is nil. For 1 again it is un. So un, nil, un, em you will be writing. That's what is according to the IUPAC nomenclature rules when these elements were not given official names, right? So I'm going to write down this as un, nil, unium. Similarly, this one will be un, nil, bium. Then un, nil, trium. Then you are having un-nil quadium. Similarly, un-nil pentium. Right? Now, the official names here is 101 is Mendelevium, then Nobelium, then you are having Lawrencium, then you are having Rutherfordium, Then you are having dubnium. Now I am not going into further details here. The thing is, I have already given you mnemonic from 104 to 118. Remember, I have given you Rutherford dubbed a song behind his metro in Dermstatium, right? And Roger can never have flavor of masala chai. That I've already given you, right? So you can refer to that. So that's the reason I'm not writing it further, okay? Now, as far as the first three elements are concerned, for them you can remember Mendeleev has done, a very good work of systematically arranging the elements in the tabular form, and that led to many things later on, right? So that's why he is a Nobel laureate, the recipient of Nobel Prize, we say. So that way only you can remember here that simply you can write down Mendeleev Nobel laureate. Laureate means recipient of it. And the thing is, see, and Mendeleev is like, kind of first scientist to give it in the tabular form. So that way you can remember first one after 100. First one after 100 is 101. So that way you can remember 101 is Mendeleevium. So Mendeleev Nobel laureate. Okay? See, if there is any other mnemonic which you are having, that's absolutely fine. I'm not just imposing this mnemonic, right? That's the way I remember. I find it easier. You may have your own. So that's absolutely fine. I hope it is clear. Now, what kind of question you can expect from here? Simply, either if their examiner is kind enough, what they will say? They'll say, okay, there is element named, like there is an element whose atomic number is 110. Its name will be. So they may ask you according to nillium kind of, right? But if they really want to test you whether you know the name or not, they may ask for you. They may not give you this option. Unnil option will not be there. Nillium option is not there. They may give you Dermstatium, they may give you Laurentium, Rutherfordium, Dubnium. So you should know that 110 is Dermstatium, right? So that thing will come from practice, and do remember this kind of question can be asked. So I hope I made very clear what is important over here, okay? So now let us go further. I hope it is written, and in fact you need not write down also. You are having your NCERT, in that you can tick mark, right? Okay, now let us go for trends of physical properties. Physical properties in periodic table. Now the first one which we are going to learn is effective nuclear charge, which we represent as Z effective. Now again it is very simple here. Suppose there is an atom which I am showing. There is only one shell to it. Nucleus here, there is electron here, right? There is no inner shell which I am showing. I remember, Sashi, I'll definitely tell you before this periodic table chapter is over. Do not worry about that. Hai? Exceptional configuration in D block, F block, I'll definitely tell you. Do not worry. Do remind me before this chapter ends. At present, we are just focusing on what is given in your syllabus there for your test. Okay? I'll be teaching you. Okay? I do remember. Now the thing is, you are having this atom, and I'm saying I'm not showing any other inner shell. I'm simply saying that, okay, only one shell is there and there is electron there. Now this nucleus is going to attract this electron or not? It is going to attract it. Let us say the force of attraction here, I am representing it by F1, right? So this is nuclear force of attraction. Now suppose, this is not the scenario always. Now suppose what I am doing is, here I am introducing one more shell, chalo. Okay? This is your nucleus. I am writing here 2 electrons. And for simplicity, in the outermost shell, I am just keeping 1 electron. Right? Now, the thing is, if at all I ask you about this force of attraction, F2. Okay? Let me tell you a few things and then you can answer. Right? First, tell me, these inner shell electrons, are they negatively charged? No? Electrons are always going to be negatively charged. This is negatively charged. This is also negatively charged. So there is going to be Like charges repel each other or attract each other? They repel each other. So what will happen? These inner shell electrons are going to repel the outer shell electron. So are they pushing it away or not? Right? So these inner shell electrons are pushing the electron, outer electron, from where? So if they are being pushed away, these are being pushed away by whom? The inner shell electrons. And so in that case, this outermost shell electron has moved a little bit far away from the nucleus. Do you agree? Due to repulsion from the inner shell electron, the outermost shell electron has little bit pushed far away, little bit I'm saying, right? So because of that, now the force of attraction which it will feel, will it be more than the previous case or lesser than? If I ask you what is the relation between F1, F2, that means whether F2 is greater, F1 is greater, which one will be greater? Correct, Tanishka. So I'm saying that F2 is lesser than F1. Right? Now, correct. F1, everybody has answered correctly. F1 is greater, F2 is lesser. Very good. Right? Now, one more thing here. Now, don't you think that these inner shell electrons are in a way protecting the outermost shell electron from the nuclear force of attraction? I'll repeat the statement. Don't you feel these inner shell electrons are trying to protect the outermost shell electron from the nuclear force of attraction? Are they shielding the outermost electron or not? Are they shielding the outermost electron or not? They are shielding it, right? They are protecting it, right? So that's what is your shielding effect or screening effect, right? The way when you move out in rain, if your umbrella is perfectly all right, then the raindrops will not fall onto your head. That umbrella is basically shielding you from the rain, right? But if at all there is some hole or something, then you won't be shielded there, right? So the thing is, this inner electrons are shielding the outermost electron from the nuclear force of attraction. Okay, that's what is shielding effect or screening effect. Now listen to another statement carefully. I am saying that basically because of the repulsion from the inner shell electron, outermost shell electron has moved a little bit far away. Hence, the force of attraction now which is felt on this outermost shell electron, it is decreased. And that decreased nuclear force of attraction only I am calling it as effective nuclear charge. I repeat it once again. I am saying because of the repulsion from the inner shell electron, outer shell electron has moved a little bit far away, right? And when it is moved a little bit far away, then the nuclear force of attraction on this outermost electron, it has decreased. And that reduced the nuclear force of attraction only, I am calling it as effective nuclear charge. So simply in your mind, what you should treat, that Z effective is nothing but the nuclear force of attraction which is felt by the outermost electron in the presence of inner shell electron. That's the only thing. People keep on, kind of getting confused there. Simply remember Z effective is nothing but the nuclear force of attraction when it is felt by the outermost shell electron in the presence of inner shell electron. That's the only case. Are we able to understand? So I'm going to write down these things here. So I'm writing the phenomenon in which outermost shell electrons are shielded from nuclear force of attraction by the inner shell electrons. Is called as shielding effect. Okay. I'll write down the another statement also. Due to repulsion from inner shell electrons, the outermost shell electrons are pushed away, and hence the nuclear force of attraction felt by them is reduced. This reduced nuclear force of attraction is called as Z effective. Okay? So please write down the previous one, then we'll proceed further. Are you done here? Completed? Okay, I'll go for the next page as well. Quickly write it, Bitam. Then I'll write down the formula here. Z effective is given by Z minus sigma, where Z is nothing but atomic number. Sigma is Slater's constant or screening or shielding constant. Copy this, then we'll proceed further. Now, here we need not learn about how sigma will be calculated and all those things, right? Simply you remember formula is Z effective equal to Z minus sigma, right? There is one more order which you need to remember. For the same value of n, when the principal quantum number is same, then the shielding or screening effect, it is seen for S, it is maximum, then P, then D, and then F. Okay? That is actually derived from some graph actually here related to some wave function or something. We are not going into details of that. Simply you remember that for S, shielding effect is best. It is shielding effect best means it is able to stop or kind of stop the nuclear force of attraction to its best of capacity, right? And D and F, poorest. They are not able to stop or kind of hinder the nuclear force of attraction. So poorest shielding effect for F, then D. Got it, everyone? Now let us simply write down here trend of Z effective in periodic table. So whenever we are learning about the trend, we are saying that basically it will be from left to right, or else it will be from basically top to bottom. Yes, Girvani, you are correct, beta. It is because of the penetrating power also we say, but that also is coming from the graphical thing only. From graph only we can identify that. Okay. Now, for Z effective, when I am moving from left to right, formula is Z minus sigma. So normally when I am moving from left to right, atomic number, which is Z, it increases by 1, right? So atomic number is to increasing by 1. But sigma, the way it is calculated, it is seen that it increases only by 0.35, right? So both are increasing, but which one is increasing more? Z is increasing. So overall, Z effective will increase. So here I'll say that left to right, Z effective increases. Are you able to understand? Left to right, when I'm moving, your atomic number increases by a factor of 1. And from the calculation part or from the Slater's rule, it is seen that your sigma, which is the screening constant, it also increases, but not to that extent. It increases by 0.35 like that. So overall, it is seen that overall Z factor is more dominating. So because of that, you will have Z effective increasing from left to right. Now when it comes to top to bottom, so Z effective almost remains constant. Okay? And in this case, you remember when I'm talking about almost remaining constant or whatever is the Z effective from left to right or top to bottom, I am telling with respect to, or the context is of S and P block. Okay. So here basically I am saying for S and P block elements. Reason being for D and F, many things changes, right? So that's the reason we are restricting ourselves. And in fact, you will see that when it comes to this periodic classification, majority of the times we are going to compare the physical properties for S and P block only. We are not going to read much about D. For reading about D and F, we have got a separate chapter for that in your class 12th. Okay? Did we write down here, beta? Everyone? Shall we proceed further? Are we done writing? Okay. Now let us go for the next property, which is atomic radius. Now, if I ask you what is atomic radius, what is that? How do you define atomic radius? The distance of the outermost shell electron from the nucleus. That's what is the simplest definition, right? So this is this distance, which I call it as atomic radius. So I can write down the distance between the outermost shell electron from nucleus, right? Now the thing is, do not think that you will be taking a scale and you will be measuring that distance. Actually, it is determined from the experimentally determined bond lengths, right? From there only you can determine. Okay, there is no other way possible. Now, next thing which we are going to learn is types of atomic radius. Now, the thing is whether I refer to a metals radius or as I am referring to a non-metals radius, accordingly the change in name, but actually it is atomic radius only. So if I say that I am talking about atomic radius for a non-metal, I should refer it to covalent radius. For a metal, I'll use the name metallic radius. That way it is given, right? So let us go for the first one here. That is covalent radius. So I'll write down just one thing. It is defined for non-metals. And here basically I am giving you an example of homonuclear diatomic molecule. When I say the term homonuclear diatomic molecule, what do you understand by that? When I say homonuclear means? What is the meaning of homonuclear? Break the words and tell me the meaning. Vamsi, example is correct, beta, but I'm asking you something. Homonuclear means nucleus is same of both the atoms, so it will be like atoms. Diatomic means two atoms will be involved there. Okay? Now, for example, if at all I'm writing here for homonuclear diatomic molecule. Let us say I am writing diatomic molecule as A2. So let us say this is A atom, one A atom, its nucleus, another A atom, its nucleus, right? Now, this is the internuclear distance which you are able to see here. Let me draw it in a better way. Are you able to see this distance is the internuclear distance between the two atoms there, right? So basically, what is your covalent radius? Covalent radius will be half of this distance. So I can say that this is RA and RA is actually DAA by 2. So if at all I have to define, how would I define? I'll define it is half of the internuclear distance. Are you able to see? This is half of whom? Of the internuclear distance, like distance between the two nuclei of the like atoms. And in what condition they are present? They are present in covalently bonded condition. So I'll write down here for covalent radius, how do I define? It is half of the internuclear distance between the two like atoms which are bonded, covalently bonded, which are covalently bonded to each other. Write this down, then we'll proceed further. So what kind of question could be asked? Maybe they can give you Cl2 molecule, right? They may give you this distance. They may ask you what is the covalent radius. Or else they may give you simply Ra, right? And they may write down something else. They may ask you which one is the parameter which represents the covalent radius of it. Okay? So make sure you are knowing this. Write this, then we'll proceed further. Written? Sandhya is done. What about rest of the people here? Done. Okay. Now, if someone who is there who is wondering, ma'am, what about heteronuclear? There also some formula is there, but the thing is that it is not of your syllabus, beta. That's the reason I'm not telling you, right? So simply for understanding this much is sufficient. I have given reference with respect to your basically homonuclear diatomic molecule. Okay? If at all it is heteronuclear, then the electronegativity also has to be taken into concern, right? Now, let us go for the second one, which is metallic radius. So the atomic radius of a metal is only known as metallic radius actually, right? So I'll say that as the name suggests, it is defined for metals. Now, if you remember little bit also from your solid state, you know that in metals there will be proper arrangement of the metal atoms like BCC, FCC, HCP, all those things are there, and we call that as the metallic lattice. So let us draw one such lattice here, simple one. We are not going very detailed or kind of. So I am simply drawing a lattice over here. It should be uniform size, and let us say these two are the metal atoms here which are present in the crystal lattice of the metal. Now this distance you are able to see, this is distance between two metal atoms, right? Now if at all I want to represent the metallic radius, so simply what I'll be doing, half of this. So Rm is equal to dmm by 2. So what will be my answer? For metallic radius, it is half of the internuclear distance between the two adjacent atoms which are present in the crystal lattice. Okay, so I'm writing here Rm, that is, it is half of the internuclear distance between the two adjacent atoms present in the metallic crystal lattice. Write this down, then we'll proceed further. So we will write down after this, which is van der Waals radius. Correct. Now when it comes to van der Waals radius, it will be defined for gases and inert gases here, gaseous molecules and inert gases. So I'm writing it is defined for gases or as gaseous molecules and inert gases. Now to understand that, let us say I'm having a sample of Cl2. Okay? So let us say this is one Cl2 molecule, this is the nucleus of it, right? Another Cl2 molecule is there in the sample. Because when I talk about sample means you do not have just one Cl2 molecule, you'll have more than that. Okay. Now these two are the neighboring molecule. Okay. Now I am saying this distance you are able to see. This is dCl2Cl2, right? And in fact, let me just write down not Cl2Cl2, let me just write down as D so that it remains simple. Okay. Now what I'm doing is, basically half of this distance, I'm calling that as van der Waals radius, that is d by 2. Let me talk about this again. I'm having two neighboring molecules, right? Now, in those neighboring molecules, you are having two atoms which are not in the bonded state. These two atoms, they are not in the bonded state. Now, if you are measuring half of the internuclear distance in the bonded state, it becomes covalent radius. I'm not talking about covalent radius. I'm talking about the internuclear distance between the two non-bonded atoms present in the neighboring molecule. That's what is basically your van der Waals radius. Are you able to understand that? So I'll write down here van der Waals radius. It is half of the internuclear distance between the two non-bonded atoms in the neighboring molecule in solid state. Now, the last line you might have seen, that solid state I'm talking about. The thing is, when I write solid state, that doesn't mean that it is defined for solid state. It is defined for gases only. But the thing is, you know that gaseous molecules are free to move around now. Then how would you measure the bond lengths there, right? So to measure that, basically, or the distance between the molecules there, you need to reduce the temperature to such an extent that it becomes solid. And then you measure it. Getting it? That's what is in solid state. In fact, there is one definition of van der Waals radius which is given in your chemical bonding NCERT, that it is the distance between two similar atoms in separate molecules in solid state. That's what is van der Waals radius. Are you able to understand that? Let us go further then in that case. Quickly write it. Did we finish writing it? Done? Okay. Now, if I ask you to compare between van der Waals radius, metallic and covalent, let me just draw a diagram for your reference. This will be metallic, suppose. This will be covalent. And this distance will be your van der Waals. Which one seemed to be maximum here? Which one seemed to be maximum? Correct, Vamsi. Van der Waals radius maximum. In case of covalent radius, there is overlapping, so that bond length will decrease there. So that's why least. In metallic radius, there is no overlapping, right? So that's the order, and you must remember it, okay? Good. You must remember that. And everyone has answered correctly. Wonderful there. Good. Now, we are proceeding now further. General trend of atomic radius, or else let me first write down the factors, then we'll come to the general trend. Factors affecting atomic radius. Factors affecting atomic radius. Now the first one is Here I am talking about basically Z effective. Now simply whenever you listen to the word Z effective, only one thing should strike in your mind, that it is nuclear force of attraction, nothing more and nothing less. Are you able to understand that? If at all somebody says Z effective is there, Z effective means simply nuclear force of attraction, you should be able to identify. Okay? So if Z effective increases, what is happening? If Z effective is increasing, your nuclear force of attraction is increasing. And if nuclear force of attraction increases on your outermost shell electron, will it be pulled inside or not? Will it be pulled little bit inside towards the nucleus or not? So what will happen to the size? Size will reduce. So I'm writing here Z effective increases, and because of that, nuclear force of attraction that will increase, and because of that size is going to decrease. Second one is shell. If the shell keeps on increasing, then the distance of the outermost shell electron from the nucleus, that will increase, and hence the size will increase, because that outermost shell electron is feeling less force of attraction from the nucleus, right? So the thing is, if n increases, then the size increases. Okay. Third point I am writing here, shielding or screening effect. And simply when I say this word, simply one thing should strike in your brain, that shielding effect or screening effect is inter-electronic repulsion. Nothing more than that. So this is representing inter-electronic repulsion. So I have to ask directly, if at all inter-electronic repulsion increases, what happens to the size? If inter-electronic repulsion increases, what happens to the size? Size will increase. That's correct. So I'll write down shielding effect increases, size will increase. These are the few factors which affect your atomic radius. Shall we proceed further now? Now let us go for general trend of atomic radius in periodic table. So I'm just writing the general trend. After that, we'll proceed for seeing specific trend in S, P, D, F block and certain periods. So in a period, when we are moving from left to right, what happens to Z effective? What happens to Z effective? Z effective increases, and because of that, size should decrease. Z effective increases means nuclear force of attraction is increasing, and because of that, size should decrease. Then, in a group, is there any role of Z effective? There is no role of Z effective. Simply things will rely on the number of shell. So top to bottom, when I move, number of shell increases, so size will increase. Done? Okay. Now let us go for specific trends here. Trends of atomic radius now. First one we are going to see in case of second period elements. Now, when I go for writing second period's element, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay? Let me include neon also. Okay? Now, when I'm moving from left to right, I know that Z effective increases and accordingly size should decrease. Right? So this goes well, no problem. Up to what point? Up to fluorine. But after that, what happens? For neon, size is increasing. Can you tell me why? Can you tell me why? Do we know the reason of that? See, if this neon is not there, then there is no problem. Simply when you are moving from left to right, Z effective is increasing and accordingly size is decreasing. So you should be aware that when we are talking about these two, we are talking about metallic radius. These two are metals there. When we are talking about them, they are all non-metals. So I am talking about the covalent radius. And for them, just now we have seen that the van der Waals radius will be defined. So because of that reason, you know that metallic radius will be more, then comes covalent radius, then comes van der Waals radius. So in a way, we can say that in their period, the inert gases will have maximum size in their own period. I'm not comparing between any random periods here. In a particular period, in a given period, the size of your inert gases are going to be maximum in their period. Okay. So I'm going to write this down here. In a given period, size of inert gas will be maximum. Size of inert gas will be maximum. Right. I hope it is clear to you. Now I am writing here, if van der Waals radius is compared for all, if the examiner specifically say that what is the van der Waals radius order for the second period element, then uniformly you are taking van der Waals radius for all of them. So in that case, normal trend will be there. That is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and you are having basically here neon. Able to get it. But if the examiner is not specifying in the question, then you should stick to the first order. If they are saying that what is the order, which is not the case, okay? Normally they go for the first one only, which I have written, okay? And normally they even avoid this. But for your knowledge, you should know that in a given period, the size of your inert gas is going to be maximum. Write this out. And the thing is, whatever we have written for the second period element, same thing is similar order is there for your third period element. That means sodium, magnesium, aluminium, like that, going up to argon. So argon will be maximum size in the third period. So I'm simply writing one statement here. Similar trend in atomic radius is found or is present in third period elements. So please write it down and then we'll proceed further. Once you are done, let me know. Completed? Okay. Now let us go for seeing the trend in S block. So if at all I talk about alkali metals here, so lithium, sodium, potassium, rubidium, cesium. I am not including the radioactive elements here. Then if I go for alkaline earth metals, which is beryllium, magnesium, calcium, strontium, barium, there is no problem in the size here. As you proceed down, the shell numbers are increasing and hence top to bottom size will increase. So simply we are going to write down size will increase. Are you able to see? This is like increasing down. So N increases and the size is going to increase. Got it, everyone? Yes, there is no exception here. It's normal trend, S block. Down the group, it increases. Okay. Now, let us go for P block here. Now, when it comes to P block, you are having group number from where to where? In case of P block, group number is from where to where? Which group? In modern periodic table, I say that it is P block. People kindly answer 13 to 18, right? Now, when it comes to exception, in case of your atomic radius, there is only one group which is having exception in their atomic radius, and that is group 13. Rest, down the group when you move, there is no problem with the atomic radius. Okay, so I'm writing here in P block, exception in atomic radius is found only in group 13. Now, when it comes to group 13 elements, what are the elements? Boron, aluminium, gallium, indium, and thallium. Right? Normally, what we may feel as we are going down, it should increase. Right? But what is actually found here? In case of aluminium and gallium, you are able to see that the radius of aluminium becomes greater than that of the gallium. So in fact, if at all I have to write down the order, it will be boron, gallium, then you are having aluminium, then indium, and then thallium. This is what is the order which we will be writing here. Right. Let us try to see what happens there. And in fact, you will see that the data according to NCERT is 143 picometer. This is 135 picometer. Now let us see what is the reason behind there. You are having aluminium, you are having gallium as 31, right? Now when it's not anomalous pair here, beta. Okay? Do not use the term anywhere. Okay. Now when it comes to aluminium, I'll be writing the configuration like neon 3s2 3p1. For gallium, I'll be writing basically argon, then 4s, 3d, 4p. This is like 18 done here, 2, 10, and basically here 30, and there will be 1. Right? Now, when it comes to gallium, let me show you this nucleus. Then you are having 3d, and this one is 4s and 4p here. I'm not showing you more inner shell. That means first, second, I'm not showing. I'm just showing the third shell, and that too holding that 3D there. Fourth shell having 4s and 4p there. Okay. Just for the understanding. Okay. Now you understand one thing. That here in case of gallium, are you able to see 10 electrons have filled up in the 3D subshell? 10 electrons have filled up in the 3D subshell. Now, do you agree or not? Kindly respond yes or no, whether you are getting it or not. I am just explaining what is happening in the outermost and the secondmost, like second last shell here. That too with reference to 3D, 4s and 4p here. So are you able to realize that 10 electrons got added up in 3D subshell, right? Now, as an atom will be electrically neutral, right? That means if 10 electrons I've added here, so additional 10 protons would have got added up in the nucleus. That we agree? Now, because of the additional 10 protons here, there will be additional nuclear force of attraction or increased nuclear force of attraction, right? So that increased nuclear force of attraction after crossing first shell, second shell, it is reaching to the third shell, right? But whom does it meet in the third shell? 3D. Is this 3D capable of stopping this nuclear force of attraction or screening this out properly? The shielding effect of D subshell, is it poor or not? Is it poor or not? Tell me there. Shielding effect, does D has a better screening effect? Kya? No. That means it will say, no, it's not my work, I can't do it, right? I'm not able to stop the nuclear force of attraction. So ultimately it reaches to the outermost where it is 4s and 4p. So ultimately what happens? Outermost shell electrons start feeling more nuclear force of attraction just because this 3D could not stop that. It couldn't screen it. So because of that, what will happen? Nuclear force of attraction is increased on the outermost shell electron, and because of that, they'll be pulled towards the nucleus little bit, and because of that, the size rather than increasing, it decreases. So ultimately, who is the culprit? It is the poor shielding effect of D subshell electrons. So that you must know. I hope it is clear now, right? So I'll write down this is due to poor shielding effect of 4f, not 4f, sorry, D subshell electrons. And sometimes it is also known as decontraction, transition contraction, like that. I hope it is clear. Is this clear to people who are here? Shall we proceed to the next one now for D block? In D block, let us go for understanding here 3D transition series. So I'm writing the elements. Right? And when you look at the configuration here, you will be having 3D1, 3D2, that means 4s2, 3D1 I am referring to. 3D3, you are having 4s1, 3D5. This one is 4s2, 3D5. This one is 3D6, 3D7, 3D8, 4s1, 3D10, 4s2, 3D10. This is what is the configuration which we see. Right? Now, what is the trend of the size here? It is seen that initially it keeps on decreasing. Then almost it is same. Almost it becomes same. Then it increases. Okay? Now one thing you should be very clear about, that there are two forces which are acting in any atom, right? On that outermost shell electron, one is the nuclear force of attraction which tries to attract it. And the another one is the inter-electronic repulsion, right? These electrons are pushing them away, right? So there are two effects here. Now you just try to relate with force of attraction and force of repulsion. So if at all these two operating forces which are existing in an atom on the outermost shell electron, just understand, I am talking with reference to the outermost shell electron. Outermost shell electron feels the nuclear force of attraction from the nucleus, and it feels the repulsion from the inner electrons. These are the two forces which are acting. Now, if I am saying that force of attraction dominates the force of repulsion, so ultimately what will happen to the size? Will the size reduce or increase? You think on that basis. At present, do not worry about what I've written on the board here. Simply tell me if force of attraction felt by the outermost electron, if that is more in comparison to the repulsion which it feels, then definitely size will decrease. What if it is the reverse one? If at all the force of repulsion which is felt on the outermost electron is more as compared to the nuclear force of attraction, so the size should increase. What if somehow these two forces are balancing out each other? Then in that case, size should remain almost constant, right? So that's what is the reason here. Up to this, you are able to see decrease. That means Z effective is dominating over the screening effect. When I say screening effect, simply take it as inter-electronic repulsion. Okay? And when I say Z effective, simply take it as nuclear force of attraction. That is the way you have to treat it. Nuclear force of attraction. Now, here what is happening? This Z effective is almost becoming equal to your screening effect or shielding effect. And here what is happening? Definitely repulsion is more dominating, so Z effective is lesser than the screening effect. Now try to understand why it is happening so. When I am moving from scandium to Mn, are you able to see that the subshell is getting progressively filled up, right? And as it is getting progressively filled up, so what is going to happen? Their shielding power is poor. So because of that, they are not able to hold on to the nuclear force of attraction for basically the outermost shell electron, and hence the size is decreasing. Now, the moment you cross 5, it is getting paired up. When it is getting paired up, so simultaneously now inter-electronic repulsions are also going to increase. So it is seen here, both these phenomena are actually balancing out each other. In the last, when it has become D10, right? So it's like completely they are paired up, more repulsion as compared to attraction, and hence the size will increase. So Jata, the entire material will not be available totally free on this site, beta, right? There is Gosalites app which you can log on to, right? And then you can avail the facility. I hope it is clear. Then one more point I'll discuss before just winding up the session. I hope it is clear, beta. As such, you'll be reading more also in D and F block. But the thing is, for 3D series, at least you remember, right? I'm not going into 4D and 5D, and even I cannot say that for 4D and 5D, the similar trend is there. Okay? Okay, let us go for the last one here. Now, when I talk about here, group 4, group 5, group 6 up to group number 12, I'm writing 3D transition series, 4D transition series, 5D transition series. You're having titanium, zirconium, hafnium, vanadium, niobium, tantalum, chromium, molybdenum, tungsten, and the elements like that, right? Up to group 12. Mind well, I have not written group 3 over here. Okay? Purposely I have not written. Now, when I move from 3D to 4D, do you agree that there is increase in the shell number? So ideally, the size of 4D transition series element should be greater than that of 3D, right? So what I'm going to write down here, radius of 3D should be greater than radius of 4D, right? But what is unusual, which is seen here, when I move from 4D to 5D, right? Ideally, the size should increase because shell number is increasing. But to our surprise, 4D and 5D, their size was found to be similar, right? What do we mean by here? Basically, this thing is applicable for group number 4 to 12 in your D block, right? Not for group 3. Now, what we are seeing here is that this implies what? Radius of your zirconium is almost same as that of hafnium. Radius of your niobium is similar as that of the tantalum. Radius of molybdenum is almost same as the radius of your tungsten. I have just written for 3 pair. That doesn't mean that for rest of them up to group 12 it is not valid. It is valid. That's the reason I have written from group 4 to group 12 it is valid. Okay? Now let us try to quickly understand what is happening in this 4D and 5D, why their sizes are becoming same even though you are having shell increasing over there, right? So let us take example of here zirconium, hafnium. Zirconium is 40, hafnium is 72. For zirconium, the configuration will be krypton. Krypton marks the ending of 4th period. So 4s2, 5s2 you are having here, okay? And 5s and after that 4d. For hafnium, when I'll be writing xenon, okay? Then 6s, 4f, 5d. So 54 here, 56, 14 here, 70, and I'll be having 72. Let us try to understand what has happened in hafnium rather than increasing the size, why it has decreased. Now for the simplicity's sake, I'm just going to show you only last 3 shell, 4f, 5d, 6s. Right? Now the thing is, are you able to see 14 electrons being added up in 4f? If 14 electrons got added up there, so definitely to make the atom neutral, you will be having 14 protons got added up in the nucleus as well. Do you agree? It is on the same line what we have understood for gallium. Okay? Here I am saying 14 electrons got added up in 4f. So in respect to that or in response to that, definitely 14 protons would have got added up in your nucleus, right? Increased nuclear force of attraction is there. Okay? Now this increased nuclear force of attraction after crossing first, second, third, it reaches to 4f. And 4f is like I'm poorest in protecting you or shielding you, right? I'm not able to, kind of shield the outermost electron, or else I'm not capable enough to basically stop this nuclear force of attraction. So ultimately, this nuclear force of attraction reaches where? 5D. 5D is like I am also your cousin only, na? You are like this, so I'm relatively better, but I won't be able to stop the nuclear force of attraction. So ultimately, after the joint venture here, where this increased nuclear force of attraction reaches, it reaches onto 6s, outermost electrons. And when they start feeling more nuclear force of attraction, so hence size will reduce. Are you able to understand? So who is the culprit here? It is because of the poorest shielding effect of your 4f subshell electrons. Getting it? So I'll write down here, due to poor shielding effect of 4f subshell electrons. I hope it is clear to all of you. Did you understand this? Did we understand? It is on the same line where we have understood for gallium, it is on the same line. Okay? In gallium, culprit was 3D. In hafnium, culprit is 4F. Got it? And the thing is, up to this, we have completed the syllabus. So for test, you can refer to this much extent, whatever we could complete, because I do not want to rush through the syllabus here, right? So whatever we have prepared, up to that, you prepare. Okay? That should be absolutely fine, right? So see you in the next lecture and wish you all the best for the test, right? Thank you and have a nice day.